about hardware-assisted tracing on ARM SoCs using CoreSight and the open CoreSight decoding library. So the goal of the presentation today is not to show you exactly how things work under the hood, but to give an overview of the end-to-end solution from trace acquisition to trace decoding. With that, the hope is that when you start working on CoreSight on your own platform, you will have an idea of the terms that are involved and how a good overview of what the technology looks like. So that way, hopefully, it will be easier to connect the dots because there's a lot of things to get right in order to do trace acquisition with CoreSight. So here today we'll mostly cover the integration that we have done with the Perf core. So this is something that's been ongoing for a little while now, and we have finished that earlier in the year. So now, as I said, the goal is to get you started quickly on your own platform with CoreSight. So we'll start with a brief overview of what the technology is. From there, we'll look at what is required to get CoreSight going on an SoC. So there's a few things to look for in order for things to work for you. From there, we'll introduce the open CoreSight decoding library, and we'll end the presentation with trace acquisition and decoding scenarios. So if you're looking online for a definition of what CoreSight is, it's very likely that you're going to get lost. There's a lot of material related to CoreSight. CoreSight is basically the name given to an umbrella technology that covers all of the tracing needs of an SoC. So everything from hardware-assisted tracing, something that we are concerned with here, but you'll also find debugging with JTAGs all the way to a user space IDE. So what we wanted to concentrate on here at Linaro is the specific part where hardware-assisted tracing is concerned. So the idea is to trace everything that a CPU is doing without impacting the processing that is happening on that CPU. There's no external hardware that is required to get that going, so it basically gives you the power of a JTAG without needing the external hardware dependencies. So we've been working on this for a little while now. We have been able to produce a set of drivers. There's a framework that glues everything together. And as I mentioned, everything has been integrated with Perf, and all of the work that we have done that is related to the kernel side of the solution is found under drivers hardware tracing CoreSight. So hardware-assisted tracing works by coupling an IP block, a CoreSight IP block called an embedded trace macrocell. So we couple that with a CPU. There's usually a one-to-one mapping between a macrocell and CPU. And once configured, there's no involvement that is required on behalf of the CPU while traces are being collected. As such, we're not impacting the processing that is done on the unit itself. The idea here is we're saying no impact, but when we're talking about a trace session, one has to be mindful of the CoreSight topology and the trace session that is currently ongoing. For example, if we're looking at a trace scenario that involves a lot of DMA transfers, then we want to be careful to not select a sink that sends trace data from the CoreSight framework to memory using DMA. That way, there would be contention on the bus, and we would obviously impact processing. So when looking at trace scenarios with CoreSight, one has to be mindful of what we're doing, so what that scenario is and how we're handling the trace data that are then picked up in the sink buffer. So there's always a way to not impact the processing units on the CPU. So this is a simple yet fairly representative depiction of what a CoreSight system is. So on the far right, we have the CPU cores, and each CPU core is coupled with an ETM tracer. The colors represent the different IDs that the tracers will be emitting packets with. So once packets end up in a trace sink, they're all intertwined, everything is mixed up, and we're using the trace IDs found in the packets in order to split the traces coming from different CPUs, and that is then processed by the open CoreSight decoding library. So, fairly simple representation of what a CoreSight system is, and yet accurate enough to give you a good representation.
Sorry.
Yes?
What are the 2 dimensions that you are representing in this way?
What? Oh, yeah.
Yes, you have 2 dimensions. It's where is the time on this?
The what? Where's the what?
You have 2 dimensions here. You have the horizontal and vertical in the square box.
This here?
Yes. Where is the time?
There's no time. The square represents a sink that accumulates the trace packets. And the trace packets are all mixed up in the sink, right? Because there's only, typically right now in CoreSight system, it doesn't have to be this way, but all the hardware is wired in such a way that there's one sink per trace session. So all the packets that are generated by the tracers end up in the same sink, and using the trace IDs, we're able to differentiate the packets coming from different processors.
Okay.
If you are looking for CoreSight online and throughout the documentation, you will stumble a term called program flow trace. So that's the name given to the format that of the trace stream generated by the tracers. The idea here is simple. So instead of recording all of the instructions that are executed by a CPU and produce a massive amount of data, we simply record waypoints. And waypoints are anything that makes an instruction pointer move from one address to another. So that interrupts the flow of execution. So if we have a range of instruction that starts here and that goes there, we don't have to record everything in between. All we have to do is record where it starts and where the instruction pointer might have gone someplace else. So with that, we're saving a huge amount of space, and we're able to collect as much data as possible. So this is generated by the hardware. And as I mentioned, it will record waypoints, so everything that moves the CPU around. Examples would be return instructions, exceptions, and some conditional branch instructions. So we give those to the OpenCSD library that we'll see later in the session, and we get back executed instruction ranges. So ranges that the CPU has executed. Using the original program image, we are able to make the ranges map and pick out the path that a CPU has taken through the code. So we'll give you an example of exactly that later in the session. So on a CoreSight system, so all of the components that are described in the reference manual are supported by the drivers that we have set out. We also have a framework that links and connects everything together to make sure that there's an end-to-end path between source and sink of the traces. The only exceptions to that will be CTI, so cross-trigger interface, that Mike will start working on later this year. So that's an IP block that allows synchronization of the CoreSight blocks or devices in the system. And there's ITM. So ITM is a predecessor of the tracers that we currently support. If you end up having an ITM in your system, I suggest to start from the drivers that we have, skim out everything that is not important, and pretty easily you should have support for ITM. So ITM is a skimmed down version of the full-blown tracer. It's an earlier generation of the full-blown tracer that we have, that we currently support. Talking about support right now, upstream we cover 32-bit and 64-bit. So between vExpress, TC2, and Juno, we are covering a lot of the use cases or the topology that one would find on SoCs on the market. So if you have an SoC, simply look at the examples that we have provided for TC2 and Juno, and with that, you should have enough information to pick out how to organize things on your own system. Because everything is different on every SoC, all of the configuration has been pushed to the device tree. So you list the CoreSight devices in the device tree along with the topology of the blocks on your specific system. And with that, if things, like when things have compiled properly, that's all that should be required to get the whole thing going. So with a proper device tree and correct addresses, things should just work. As usual, the devil is always in the details, and CoreSight is no exception. So you will have to keep in mind clocks and power management. So CoreSight devices are always found on the AMBA bus. So the AMBA clock has to be listed in the device tree and manageable using the Common Clock API. If you have that, the CoreSight drivers will do the right thing with the clock, enable it and disable it when it needs to use it. So that part of the business should be fairly straightforward if, as I said, your APB clock is handled by the Common Clock API. Something trickier to handle is the power domain, simply because the blocks will be split in more than one power domain. So everything that is not a tracer, so we're talking about a funnel, a replicator, and all of the sinks, those will typically be found in the debug power domain. And all of the tracers, the ETM macro cell, those will be sharing the same power domain that the CPUs they are coupled with. So typically, you'll have the tracers sharing the same power domain or the cluster power domain that the CPUs are also sharing. And that is a problem, simply because when CPU idle decides to put a tracer or a CPU to sleep, power to that power domain might be switched off, and everything that was happening as well in that power domain also goes away. So everything, all the configuration that we have, trace data, all that is lost. So currently, upstream, there's no solution to synchronize operations in a power domain that is shared between a device and a CPU. Lina is working on that. She should have a solution very quickly. But until that happens, there's simply no other way to deal with this other than introducing your own synchronization mechanism. Now, in that area, I decided not to do anything for both reference platform. I thought it was better to not do anything and simply disable CPU idle when playing with CoreSight than introduce a synchronization mechanism that is specific to these two platforms. Then you would have to understand those, take those away, and introduce as your own. So I just decided to leave things as they are, disable CPU idle, and wait for the real solution to be available. So I definitely recommend that when you do start playing with CoreSight, disable CPU idle. That will save you a lot of grief. That way will get you going with the technology. You'll understand how things work. And once you're fairly stable and acquainted with things, you can start thinking about how to synchronize operations in the power domain that is shared between a CoreSight block and CPUs. Okay, so let's say that we have either found a synchronization mechanism or we have disabled CPU idle. Everything works well in a device tree. The system boot, all of the tracers will tell you that they are alive by printing out the successful initialization and the versions that they are. So the top portion of the slide represents Juno booting. So on Juno, there are 6 CPUs. All of the CPUs are fitted with an ETM4 tracer. The bottom part is all of the devices that have been found at boot time are listed under the CoreSight block under sysfs. So if you don't have access to the device tree, or you don't know or don't remember the addresses or how you named your devices, simply look at the devices that were discovered under sysfs and you should be set. So that doesn't go away. It's always present. It's static in the system. So now that we had drivers and a framework, we recognized pretty quickly that configuring CoreSight was very difficult. So there are dozens of registers to get right just for even the most simple session. So integrating with something like Perf was desirable because Perf is already geared toward tracing. It's ubiquitous. People know about it. And it hides a lot of complexity that people shouldn't be dealing with just to get harder tracing going. So we hide a lot of the complexity behind Perf, and whatever is not handled by Perf, we simply push to OpenCSD, and that way there's very little I can't say knowledge, but there's very little that people need to know in order to quickly get started with CoreSight. How we did this. So when we're talking about Perf, there's this concept of performance management unit, or monitoring unit, I should say. So what we did is represent our tracers as PMU to the Perf core. From there, Perf is simply not aware that it's using CoreSight. It's like any other tracer. You hide the functionality or the hardware-specific bits behind interfaces, behind an operation structure, and the Perf core just works seamlessly. That also allows us to control very tightly when the tracers will start and stop tracing. That way you're not impacting by all of the background noise that is also happening in the system at the same time. You're only picking up the traces that pertain to that specific session or process that you're tracing. So there's no interaction that is required from the users to get that process going. So when the CoreSight framework gets initialized at boot time, it will simply register this new PMU with the Perf core, and from there, everything is available using the Perf tool on the command line. CSETM is the name that we have given to that new PMU, and this is listable on a system with all of the rest of the events. So all of the events that have been configured on at compile time in the kernel are found under sysbus event source devices. So you'll also find there, as I mentioned, because it's registered seamlessly by the core at boot time, the CS underscore event, and in there, all of the typical entries for a PMU, along with a symbolic link for each of the CPUs that you have in the system. We did this because, from a Perf tool point of view, there's no way to correlate a CPU with a tracer. That way, with a symbolic link, we simply know the CPU we are working with, we look at the symbolic link, and right there we have the configurables for a tracer. So with that, we pretty much covered all of the kernel side of the solution. There's not a whole lot of material there, but everything is has its functionality. With this, we introduced the Open CoreSight decoding library. So that's a joint effort between ARM, Texas Instrument, and Linaro to basically bring the capability to decode any CoreSight traces generated by the framework with a standalone library. So OpenCSD doesn't need anything to work. It just works by itself. All right? It's on GitHub. It's public. Right now, the formats that we support are ETMv3, ETMv4, PTM, and there's also support for the MIPI protocol, which is the output that we get from the STM CoreSight block. DAT2, as I mentioned earlier, has been integrated with Perf, so if you want to get going quickly or have an example of how this can be integrated into your own tracing solution, simply look at what we've done, and you'll get an example of how things can be done. If you want an in-depth presentation or information on how the library works, Mike has written a very good blog post earlier this summer on the Linaro's core dump blog. So the link is there. That will get you a lot of information on how the internal of the library works, and it should get you a good point, as I mentioned, if you want to roll out your own decoding solution. Okay, so we have drivers, we have a framework that connects the whole thing together. Everything has been integrated with Perf. We also have a library to decode traces. We basically have everything we need to start doing our trace sessions. So putting it together is not really hard. There's just a few steps to follow, but we only need to get things right. So the first thing to do is to start with the Open CSD library on GitHub. Please stick with the master branch. That's where we have our code nowadays. All of the stable revisions are tagged, so that works exactly like the mainline kernel. And there's also a how-to there. We put a lot of time and effort in the how-to. Read the how-to. It explains how to compile everything, how to put everything together. It also gives you extensive information on how to use the technology by giving you examples for that specific kernel revision. So I emphasize on kernel revision because the perf tools are not all upstream. And if you're looking at the amount of patches that are going into perf tool with every kernel revision, it's astonishing. So last time I checked was 800 patches. So with that, because as I mentioned, our code is not all upstream, the solution kind of moves in user space based on the churn that is going in. So with each kernel revision, we rebase the patches, we make sure that things are working, maybe adjust a few things along the way. So that's why right now we still keep kernel revision along with the versions of the OpenCSD library. So this is just temporary. We will be dealing with this. The process has already started. It's just a matter of time before everything is upstream and available. Okay, so you download the revision of the library, the latest and greatest. Simply follow the how-to. I'm explaining this slide here because it's easy to miss, and a lot of people have missed it. So because perf, or the OpenCSD library is standalone, we need to tell the perf tools where to find the capability to deal with CoreSight traces. And we do that by compiling the library and using an environment variable, so CS trace underscore path, that points to where the SOs are. So with that, if everything, the perf tools linking script will look for the SOs, link the functionality, and everything works properly, you will end up with what we see at the bottom, the CS ETM decoder. If something is wrong or you're not using the OpenCSD library, you'll end up with the stubs, and obviously you can't decode anything with that. But the perf tools, the compilation of the perf tool, will still be successful. So again, when you are integrating with the OpenCSD library, when compiling the perf tools, always make sure that you hit CS ETM decoder. That will be a proof that you got the required capability to decode the traces. So because we have integrated with the PMU framework, so using that from the perf tools is like using any other tracer. So the top line, perf record -E, the name of the event, the specifics for that session, and how you want to trace the process on that, for that specific session. So when we're looking at the most simple form for CoreSight, so perf record -E, CSETM, the name of the sink where we want to see the trace data go to, and the specifics for the process. Again, I emphasize on the CoreSight devices on the system are on their sysfs. So simply take a name from there, put it into the configuration area, and from there, perf and the core framework will do all of the configuration along with the linking between the CoreSight devices that are required for the trace session to go smoothly. When we're talking about hardware-assisted tracing, CoreSight no exception, there's a huge amount of data that gets collected. So it's important to skim out the portion that we're not interested and really zero in on what's is relevant for that specific session. So there's a few ways of doing this. The first that we'll be looking at is using the mechanism that the perf core gives us. So by adding a U or a K at the end of specific options for each event, we're able to isolate traces to that specific area. So if we add a U, we're getting traces only in user space. If we have a K, we're only getting kernel spaces. All right? If you're not doing anything, then the whole thing is traced. Even with that, we recognized that we still had way too much information and decided to introduce the notion of filters. So filters on perf is already available for trace point events. The scheme was simply enhanced to accommodate filters for hardware tracers. So there's two types that we've introduced, address range filters and start-stop filters. So the first example here, address range filters, basically add the dash filter, so that's a perf thing. And after that, you specify the filter that you want to use. So in this case here, the keyword filter was added. So that was not my favorite choice. I would have liked to have range, but when you're working upstream, you can't have your way all the time. So filter it is. You specify where you want to start from, and then how many byte to trace. So using the K option, the address that you will have there is specifically, or it's typically something that you would find in the system.map file when the kernel gets generated. So in user space, it's a little bit different. So again, we have our -- filter. We're using an address for filter, so we're having the filter keyword. So the 072C here is a relocatable that you would typically find on the output of object dump. All right, so that's the offset from the beginning of the binary. Again, how many bytes you want to start, you want to trace for, and we add the complete path to the library on the system, library or binary. So that is used, is correlated with the information that we get in the perf.data file that pertains to the mapping of the events in memory. Okay? So when we're dealing with address range filter, if we have obviously a range, so it starts here, it stops there. But if the instruction pointer happens to move out of that range to go do something elsewhere, everything that happened elsewhere will not be traced. Tracing will resume when the instruction pointer comes back into the range that was specified. So that's for the address range filtering. When we're looking at start and stop filtering, if we take our example again, everything that the traces will be generated when you start, when the instruction pointer is equal to the start address, and will stop when obviously equal to the stop address. So everything that happened in between, whether it's in that function or not, gets traced as well. So there's it's a lot more inclusive, but also has the potential to generate a lot of information. So by combining, or by refining a trace session with these two filters, it's fairly easy to go down to the portion of the code that you're really interested in. So here we have, again, our -- filter. The specification of the filter is a little bit different. We have the start and stop, so that's fairly obvious. What I'd like to bring attention to is the bottom example where I've decided to start tracing in one library and stop tracing in a different binary. So that's on purpose, right? It's just to show how flexible this scheme is, right? There's no real restriction on the address or the range that you can trace. If the address exists and the binary is available on the system, you can trace it. The only limitation that we have with address filters is that we cannot use address range filtering and start-stop filters in the same session. So we've decided to keep that separately for now, okay? And there's also the amount of address comparators that are implemented on that specific SOC. So address comparators, the amount of address comparators will give you how many filters you can use for that specific trace session. So at one point, if everything goes well, you're tracing, and then the next trace session, you decide to add a filter and you get an error, that means that you've exhausted the amount of filters that the hardware is capable of supporting. Okay, so let's start looking at the decoding part of the business. So everything is working with Perf. We have a trace session. Because we are using the Perf framework, all of the trace data, along with all of the events that happen during a session, will end up in the perf.data file. So this is nothing new. We've added samples to the data that were collected by listing the packets that were gathered during the session. So if you are starting with CoreSight, you want to know if something happened during that trace session, simply dump the content of the perf.data file, and in there at the very bottom, you'll see all of the packets that were generated for that session. Now, packets themselves don't give you much in terms of what happened. It just tells you that something has happened. It's a good debugging tool to tell whether something is alive or CoreSight is alive on your system. So from here on, we'll go over the rest of the material using this very simple example. So what we'll do is we'll have a little main that calls a function in the library somewhere, and that function simply iterates over a parameter and returns the value that it has added. So the idea here is that we have a main, we're tracing the main, but we only gather statistics and trace data for what's happening in the library on the system. So very simple, and yet fairly close to what people might want to do in terms of tracing in user space. So the first thing is to get a handle on our library, call object dump on it, and look for CoreSight test 1. So you take that address, how many bytes you want to start from, or you want to trace for, and you feed that into our command line. So the middle of the screen there, we have the same call that we've seen earlier in the session, and we are asking Perf to record everything in the library in the process main on all of the CPUs that the scheduler decides to put that process for that session. So Perf will go about doing its business. It will do the configuration. It will also start tracing when the process gets scheduled by the system. And in the end, you will end up with a trace data in the perf.data file. And here we have collected about 8K of trace data. Now, it's possible to do trace data or to decode the trace data on the system, but typically what people will do is package everything that was collecting during that session, feed that onto a host elsewhere, and do the trace decoding there, which is what we'll be doing here. So obviously, perf.data is important for trace decompression, but also the .debug directory. So why the .debug directory? What does that do? In there is all of the libraries and binaries that were involved in the trace session. So this is inherent to Perf. This is one of the advantages of using Perf. So we don't have to guess all of the binaries or libraries that were involved in the session. Everything is collected for us by Perf. The only thing you have to do is harvest the .debug directory, package that with the trace data, and you're all set. You'll be able to do the decompression off the target. So here we have our kernel symbol, so that's the exact same thing that you would find in the system.map file. You have the VDSO. The main was involved. We have the loader, obviously, libc, and on top, on the right side, the libtest. Okay, so all of this is gathered by Perf, so you don't have to do anything else there. So when we're off system, the first thing to do once we've extracted our trace bundle is to usually call the perf report. So perf report will give you a flame graph of the hotspot that were hit during the trace session. Now perf report is already included into the perf tools, and it's highly generic. As such, it will give you or it will do the report based on the start of the address range. It doesn't tell you anything about what happened in that range or where that range ended, right? So for that, we need to look at, we need to decompress traces further. So trace report is a good place to start, but it's only giving us a portion of what really happened during the session. For that, perf script is the next step up. So in its simplest form, perf script will give us the ranges that were executed by a CPU. So the address in blue are the relocatable addresses that we have seen in the object dump output earlier. So if you look at these addresses and you follow the assembly language that we've had, you'll see exactly how that loop was added or was done in the function. The left part of the address is where the library was mapped in memory by the loader at runtime. And this is given to us by the mmap2 record that are embedded in the perf.data file. So using the name of the binary, we're able to get the address. We add the two together, and we have the exact address in memory where the instructions were executed. So everything, a whole lot of that is handled automatically by perf. All that information is there. We simply have to use it. So when we're talking about trace decompression and perf in general, the real power comes from the scripting capability that it gives you. So with the perf script, ends where perf is involved. If you want to have more information or you want to go into more details into what happened into the session, you're definitely going to have to do some scripting. we've provided two scripts. One script that dumps the ranges in the more user-friendly way, like we have at the bottom here. So we see that the range, exactly the range that were executed. And we also produced a de-assembly range. So another a de-assembly script that gives all of the assembler instructions that were executed during the trace session. So I'm listing how how I'm calling the scripts simply because the mechanism to doing that with Perf is a bit murky. So that's the range script. So the de-assembly script is really where we see the power of CoreSight and trace decoding. So for each range we have the output, so where this was executed from on the CPU, and all is the assembly code that was executed. The next range, and so on for the entire, all of the packets or all of the ranges that were collected during a trace session. So this is the output of the de-assembled script that is also available on GitHub. It also shows how much information you can get out by scripting. And that the assembly script was programmed by Tor in about 2 hours over lunch in a workshop week that we had earlier this winter. So by not investing a whole lot, you can get a lot of information out of the trace data that are synthesized by the Perf framework. Okay, so obviously, because I only have 15 minutes here, there's a whole lot of things that I'm not talking about. I've only showed examples that are in user space. If you want to use kernel space, obviously it's possible, but be mindful that the VM Linux is not carried in the .debug directory. So you will have to package that with the trace data that you're taking off system, okay? There's also a snapshot mode that's inherent to Perf. So that is to trace over very long periods of time and look for glitches. So if at one point you have a glitch, you simply send an event and you will get all of the dump for the extent of the size of that buffer. But those are details. I mean, if you're interested into snapshot mode, things are documented properly, simply use them. So this is to highlight that, yes, there's a snapshot mode and it's been implemented and supported. By design, everything that I've shown today in terms of how the command line works is available on Intel PT, right? So if someone gets familiar with traces on either platform, it's easy to go from one side to the other. You don't have to reinvent trace collection or how you're handling trace data. Everything is seamless in both platforms. Everything that, the solution that we have on CoreSight is heavily dependent on sysfs. So if you are rolling out your own trace solution, you will have to interact with sysfs a lot. So if that's the case, simply look at the examples that we have provided, and that should get you going pretty quickly. And as I mentioned, we are feverishly trying to finish upstreaming the solution. There's only a small portion of the user space tools that have to be upstreamed. Everything that is not upstream is found on GitHub. I rebase the patches with every stable revision and make sure that for that revision, things still work, okay? And yeah, as noted earlier today, the cross-trigger interface driver should be coming up shortly. It's just a matter of time before it happens. So this is a team that has been working with me on CoreSight over the last little while. Chinian, Mike, and myself are here all week. If you have any questions, by all means, stop us in the corridors, and we'll be happy to help you to the extent of that we can. And now it's enough for me. It's now time for you to ask questions. Yes.
I've got a couple of questions, if that's all right. So I was a bit surprised that there aren't any 96 boards being enabled. Is there a reason for that? To get like more people using this, it would be good. It would be good to have like High-Key or Dragon board enabled.
So the initial intention was to use the 96 board products, but for some reason, for different reason, it didn't happen. Whether the silicon was not ready or the code was not ready. And we had to settle for platforms that were already available. So that was our original intention. It did not happen. But nowadays, if someone's interested, they can always try. As I mentioned, the clocks and the power domain are always a problem when working upstream. It's always a matter of getting those, the code for those to support that upstream properly, and then CoreSight will just work.
And what does the CTI support bring in terms of features?
CTI is a way for IP blocks to synchronize themselves. So if a buffer gets full and we have a CTI driver that's wired properly, it can tell the tracers to stop sending information.
Okay.
Without intervention. Right? Otherwise, you would overflow your buffer, which is what's happening right now.
Yeah, okay.
So in those situations, in the buffer, you will get the latest trace data. So you will only lose the farthest portion of the trace data that are least relevant to the case being traced.
Okay.
I have a question. So the OpenCSD, can it be used independent of Perf? Like, for example, I'm storing all the sync to put a sync.
You have to get the microphone closer to your mouth.
Oh, okay. Better? Okay, the OpenCSD library, can it be used without using Perf?
Oh, absolutely.
So
OpenCSD is a standalone product,
Okay.
right? We've integrated with Perf simply to give an example of the integration of the library into an end-to-end solution.
So you just need to get the data from the sync and then provide it to OpenCSD and get that thing out.
Exactly. You just have to find a way to feed the packets to the library. And the library is not even aware that it's part of Perf,
Okay.
or that's being linked with Perf. There's a set of CAPIs that you can link against, and from there, you're just using the functionality provided by the library.
Okay. Thank you.
Is CoreSight in any way connected with GDB, and can it work with GDB?
Work with GDB?
Yes.
Not yet.
Is there plans or a need?
Omer, would you like to answer?
There was initially a plan, but still it's not somewhere, in discussion even. So I don't know if in future maybe, but at least there is a talk about it to enable GDB and LLDB to use it, but still there was initially the lack of hardware was one of the problem. But I don't know if GDB has plans. I cater towards LLDB and they still don't have a plan for it.
Yeah, it's in the work, various states but just not there yet.
Also, too, what events can you trigger a trace on? In other words, I know that you mentioned events, but I didn't see.
What do you mean by what event?
For instance, read writes, interrupts.
So this thing does not work with events. It works with addresses. Right? So if you have an interruption that you're interested in, simply look up the address of the interrupt routine, feed that to the perf command line, and whenever the instruction pointer hits that address, traces will be generated. So it's not an event-based mechanism like you would get for interruptions, for instance. Everything works with an address scheme and an explicit start of the recording of the trace data.
So do you find that it's difficult to keep up, for instance, when the perf is trying to pull data out of the trace buffer, and you're running something on another core that's running at speed? At what point will you basically no longer be able to keep up?
That's obviously platform dependent. It's based on the use case that you're working with, how fast the CPUs are going and things like that. I haven't been able to bust it. I haven't been able to bust a solution. So I found that it's a zero copy mechanism, basically. There's no copy between what the trace data collected in the kernel and the rendering in user space. So Perf will give you an mmap buffer, and that buffer is shared between user and kernel space. The only problem is the processing of the indexes in that ring buffer. And as I mentioned, I haven't been able to bust it.
On the hardware, on the Juno?
Yes, right. It's just that I don't have the right test cases, the right load to do that. I'm pretty sure that if someone with real test scenarios on a heavily loaded system, at one point, given the right conditions, we'll be able to get to the end of that. And when that happens, basically, the setup of the tracers in the perf core will fail. And when that fails, the thread will simply put back into the queue. So you're not losing that processing. It's been implemented that way for specifically something like that. So scheduler will do its thing, something will happen in the system, processing will go on, and then at one point that process will be up again. So it will be placed on the CPU. Before it's being placed on the CPU, the tracers will be set up, and part of that setup is looking if the user space had had time to consume the data that was last written. If you're expiring the buffer, so we're going back to our condition, so the setup fails, that process goes back into a queue. So you're not losing the data. The setup, the processing that is associated with that time slot does not get wasted. It will simply be put back into the queue. The same way that your process happens, the same way that happens with your process on a heavily loaded system. Plain and simple. Good question.
Have you played at all with using the CoreSight with an external debug agent like JTAG? I know OpenOCD supports some versions of like their ETM. I was just wondering if you've looked at that at all.
So there are solutions out there that will set up CoreSight using an external interface. We simply haven't integrated with that, and we don't. There's no integration with, or there's no plan to integrate or synchronize, I should say, with an external tool. It's one or the other, basically.
Yeah, okay. Because you could
Otherwise
imagine you
it
could
becomes a
have it then
nightmare.
event-based.
It would
I guess
become a nightmare.
You could have GDB set breakpoints that when they're hit, sets up tracing.
No, you go crazy.
Yeah.
Here.
Can you provide a little more detail on the MIPI interface that you mentioned?
Well, the MIPI protocol is generated by the STM block, and that protocol is supported by the Open CoreSight decoding library. So there's no, I don't have the specifics for that because it's part of the decoding protocol of the library. If there's anything very specific that you'd like to see if it's supported or not, I would definitely ask. Mike is definitely the better person to answer that. I don't know if you have a specific question about.
Just general. I was just generally curious about how it works or how data is throughput.
Talk to Mike. He's. All right, I guess it's time for lunch. As I said, we're here all week. If you have any questions, come and find us. We'll be happy to help you. Have a good day.